A concept closely related to p-value is significance level, which we'll denote by beta. A p-value you calculate, but a significance level you choose. So let's explain what a significance level is by the school example. So a school inspector does not want to accuse the school wrongly for being cold. So let's say that the school inspector is prepared to accept a risk of 5% to wrongly accuse the school of being cold. Then you say that you choose a significance level to be equal to 5%. The lower significance level the school inspector chooses, the more secure the inspector wants to be that he or she does not accuse the school wrongly for being cold. Typical values of a significance level is between 1 and 10%. You often use a significance level when doing hypothesis testing, and that's a method of determining whether a hypothesis is true with a certain significance level. And the hypothesis testing is done in 4 steps. First, check that the mean or the estimate of the proportion or probability is normal distributed. 2. Decide on a hypothesis you want to test. And 3. You choose a significance level. And 4. Conclude that the hypothesis H is true with the significance level B if the inequality in the table is true. Let us see an example that performs these steps. Assume that the temperature in a classroom in a school is normally distributed and with an unknown expectation value and known standard deviation of 1, so it's equal to 1 degree Celsius. The school inspector wants to investigate the hypothesis that the expectation value is lower than 20 degrees. So here we have mu0 equal to 20 degrees. That is the border between cold and warm. So the inspector wants to investigate if this hypothesis is true. And he or she chooses a significance level of 10%, which means that the risk that the school inspector wrongly accuses the school of being cold should be less than 10%. Then, if you look at the hypothesis testing table, then you have the hypothesis here. And then if you investigate an expectation value with known standard deviation or with unknown standard deviation, or you investigate the probabilities and proportions. In our case, we investigate an expectation value with this kind of hypothesis, with a known standard deviation. So you see our hypothesis corresponds to this one, and known standard deviation, so this one here we want to investigate. That is this inequality here. For beta equal to 10%, we have that set beta, according to the table, is equal to 1.285. Thereby this inequality becomes, and we assume that the school inspector inspects 10 classrooms. So here we put 10. So the inequality becomes this one, that is this one. That means that the school inspector will conclude that the school is cold if he or she gets a mean of the sample less than 19.6 degrees. Then assume that for a sample of these 10 schools, the inspector got a mean temperature of 19 degrees Celsius. Since 19 is less than 19.6, the school inspector concludes that the hypothesis is true with a significance level of 10%. So the risk that the school inspector will accuse wrongly the school of being cold is less than 10%. Note that we previously have seen that for this sample mean we got a p-value of 0.08%. And that means that the risk that the school inspector, given this sample temperature, wrongly accuses the school of being cold with a probability of the most 0.08%. So if he or she is prepared to accept a risk of 10%, then it must be less than 19.6. In actuality, it was 19. That means that the risk is less than 10%. And even more than this, we can say that since the mean was 19 degrees, the risk that the wrongly accuses the school of being cold is less than this one here. So the p-value tells you more, and the significance level just is something you choose, that you say you want to be less than this, but in actuality it was even lower than that. Let's just briefly sketch the logic behind this table here for hypothesis testing. We use the example with the school to explain. So if you consider the mean and take that to be normal distributed with the expectation mu and standard deviation sigma divided by square root of n. Given that the expectation value is right at the border between warm and cold, that is 20 degrees, then beta is the probability that the mean will get an outcome lower than this, since we have set beta here, which we can see from this figure, because here we have the mean and here we have the expectation value in this case. Then the probability of getting this red part is beta, and this point here is this one here, since we are set beta standard deviations away from the center. Then, if the expectation value is this mu0, the border temperature between warm and cold, the probability of getting a mean lower than this, which is this value here, is equal to beta. So if we get a mean in this interval, we say that the hypothesis is true with the significance level of beta. So that basically means that we got something that only happens with the probability of beta or less, given that the school is warm. A bakery bakes cinnamon buns, and let x be the amount of fat in one cinnamon bun. It has an unknown expectation value and standard deviation. The bakery claims that their cinnamon buns have less than 10 grams of fat, so this is mu0. However, a customer suspects that the cinnamon buns contains at least 10 grams of fat in average, and therefore orders 9 cinnamon buns. And those 9 cinnamon buns contains 10.11 grams of fat in mean with the standard deviation of 0.35 grams. So it seems that the cinnamon buns contain more than 10 grams. However, this could just be a fluctuation. So to be sure, the customer wants to test the hypothesis that the amount of fat is more than 10, with a significance level of 5%. Then, according to this hypothesis table, with this hypothesis and sigma unknown, we should investigate this inequality, that is this one, with 7 degrees of freedom. Then according to the table, T beta is equal to 1.89. Then this inequality becomes this one here, and this right hand side is approximately 10.22. So we see that inequality is false. And that means that the customer cannot conclude that the cinnamon buns contains too much fat with a significance level of 5%. Note that the customer can neither conclude with a significance level of 5% that the cinnamon buns contains less than 10 grams of fat. Because to conclude that, this inequality had to be true. And this is not true for the sample the customer got. So with a significance level of 5%, the customer can neither conclude that it contains too much fat or too little fat. So if the customer wants to conclude something more definitive, then he or she needs to choose a larger sample size, that means testing more cinnamon buns, or choosing a larger significance level. And the smallest significance level they must in that case choose is given by the p-value, which is given by this one. And by changing the mean to a t-distribution, the probability is for t be larger than or equal to 0.94, which according to the table is 19.72%. So the small significance level with which the customer can conclude that the cinnamon buns contains too much fat is 19.72%. A girl wants to examine if a coin is fair. That is, if the probability of getting a heads or a tails is 50%. Let P be the unknown probability to get heads. To test that, she throws the coin 1,000 times, of which 525 are heads. So her estimate of the unknown probability is 525 divided by 1,000. That is 52.5%, which is the point estimate of P. What she really would like to do is to find the probability for the unknown probability to be 50% given 525 heads in a sample. However, this is not easy to do. because it depends on what kind of background information she has. And also the probability to get an exact value like 50% is 0. But what she can do is to calculate the probability to get at least 525 heads, given that the coin is fair, which is the p-value. And if the p-value is small, then there is a low probability for the coin to be fair. However, in this case, we actually need to take into consideration that we could, instead of getting 25 more heads than 500, we could also get less than 25 heads. So in this case, the p-value is actually this one. That is the probability for having at least 525 heads or less than 475 heads, given that the coin is fair. So it fluctuates more than 25 up or down. And this we can write more mathematically like this. The probability for the estimate to be larger than or equal to 52.5% or less than or equal to 47.5%, given that probability to get heads is 50%. Since n is larger than or equal to 30, then the estimate of p is normally distributed. So we can therefore change from this variable p estimate to a standard normal distribution set. So we have a probability of this type, the estimate larger than some value c. We can change to this one. And similar for the other types of inequality signs. So our formula here can be written in this way. So here we have separated for larger than 52% and smaller than 47%. And we have changed from the estimate to set. And now we can replace p here and here with the 50%. And at the same time remove the given part, which becomes this one, which in turn can be simplified to this here. And here we can use symmetry to change this one to that. And then we have two of the same. And according to the table, equal to this, equal 10.42%. That means that the probability is 10.42% to get more than 525 coins or less than 475 coins if you throw a coin 1,000 times, given a fair coin. And since we got 525 heads, that only happens with 10% probability if the coin is fair. So this is a rather low probability. So we can conclude that the coin is not fair with a p-value of 10.42%. But so far we have not tested a hypothesis. So we could also hypothesis test now. But okay, since we got the p-value, then we have enough information, so we don't really need to do a hypothesis test. So we want to test the hypothesis that the coin is not fair with a significance level of 10%. Since we found out that the p-value was larger than 10%, we know she cannot conclude that it is not fair. But let's assume that you haven't calculated the p-value yet. Then looking at the hypothesis table, we see that our hypothesis stands here, and we are testing p. So we need to test that either this one is true or that one. That is these two. And if at least one of these are true, she can conclude that the hypothesis is true with a significance level of 10%. The probability table gives that set beta half, and here we should have beta half as the index here. So it's not set beta divided by 2. We have beta half, and that's 5%, which is this one according to the table. The left inequality then therefore becomes this one here, which simplifies to this. And since this is false, we also have to check the other one, which is this, which can be simplified to this. And this is also false. So neither of them was true. That means we cannot conclude that the coin was non-fair with 10% significance level. And that we already knew from here, because if we should have concluded that, then we would have needed to take a significance level larger than or equal to 10.42. So we cannot conclude it is false with 10%, but with 10.42%. With theoretical calculations, Mr. Spock has come to the conclusion that the probability for there to be life on other planets in the universe is 10%. He wants to investigate if this is really true, and therefore decides to visit 100 randomly chosen planets. But he doesn't find life on any of these planets, so he seems to be wrong. But he doesn't like to be wrong, so he makes a hypothesis test to see if he, despite that, cannot claim that to be right. So can Spock conclude that he is right with a significance level of 5%? And this is a hypothesis test of an unknown proportion, p. Note that I cannot confirm that the probability is exactly equal to 10% by doing a finite number of observations. But you can conclude with a certain probability that the opposite is the case. That is, that p is not equal to 10%. Spock therefore examines if he is wrong, so he investigates this hypothesis. Therefore, according to this hypothesis table, he needs to check this condition here. That is this one. Here p0 is 0.1 and set beta half is half of this, so it's set 0.025, which according to the table is 1.96. His estimate based on his observation was that 0 out of 100 planets, 0%, contain life. Then if you first check this one, for example, we get this inequality here, and the right hand side is equal to this. And this is true. So that means that one of these are true, so we don't need to check the other one. Therefore he can conclude that p is not equal to 10% with a significance level of 5%. So with the significance level of 5%, there is not life on 10% of all the planets in the universe. He can also calculate the p-value. Note that the estimate of p deviates from p0 by 0.1. So you want to investigate the probability to get an estimate that deviates with plus or minus 0.1 from 0.1. So we get contributions to the p-value of both sides of p0. Note that this probability can of course be less than 0, but since we are using that the estimate of p is approximately normal distributed, we need also to take contributions from negative p estimates. Then according to addition rule, we can sum these two, giving this sum. And here we can exchange the normal distributed p estimate to the standard normal distributed set. And then we get this one here, where we have replaced p in the given part here and here, giving this. And here we can use symmetry. So the symmetry, this is equal to that, so we got two of these. And this one, according to the table, is equal to this, which is 0.08%. So the p-value is 0.08%. So if there is life on 10% of all the planets in the universe, then the probability is at the most 0.08% to get the data that Spock got, that is this data, that no planets contain life. He can therefore conclude with a large probability that he was wrong to say that 10% of the planets in the universe contain life.